Okay, thank you very much for the invitation. I'm a bit outside this community, therefore I find it's especially challenging and interesting to talk now to you. I think even this kind of mixed audience physics and harmonic analysis is possibly able in a better way to appreciate what I did than the usual probability community, because it has very much to do with the spectrum of the random Schrödinger operator, but it comes from a somewhat different angle. I started many years ago with the interest in branching processes in a random environment. And the question after a long time, where's the main mass of the many particles which have been created over the time? And if you take expectations there, then you end up pretty quickly at the heat equation with random potential, which is the Schrödinger equation without I. And then I studied this time-dependent equation, and then I saw in order to get really interesting and detailed information about the branching process picture, I need to understand the spectrum in large boxes. And this is what I'm going to explain to you now today. I want to look at the usual random Schrödinger operator on ZD in large boxes. And I want to look at the boundary of the spectrum and want to derive a lot of detailed information, for example, about the precise probability distribution of eigenvalues, about also localization of the eigenfunctions, and where are they description in terms of probability, and so on and so on. And this is what I'm going to explain to you now. I chose one particular distribution for the potential distribution of the random Schrödinger operator, which stands for one bigger class of random distributions there. Actually, there are only 4 different ones with respect to the time to infinity picture, because there are 4 different, I call it, regimes or maybe even classes of distributions which end up with 4 different kinds of pictures. And I could give you now one of these classes, and I will comment later also on the other 3 ones. And this is one, I'm a probabilist. This means no minus sign in front of the Laplace operator, excuse me. So what you call deep valleys are high peaks for me. Yeah, and these are the most interesting ones for me. So I'm looking at the potential psi in a large box. Maybe I give you already the picture that I have in mind. By the way, I never did computer summations. So my pictures are not coming from computer summations, but from my imagination and my wish, what should be true, and of course of the things that I have proved. Yeah. So the picture that we should have in mind with the rest of the talk is the following. So I can make pictures only in one dimension. So this is ZD, so to speak, and you take a large box with diameter 2L. And now I give you one realization of my random potential, which is i.i.d on ZD. So don't get confused if I write it as a line. This has only a meaning that I can do it better than putting lots of separate points. Yeah. And it doesn't mean that there's any kind of continuity. But this is my way to write down pictures. So you have something like, so my potential is positive all the time and has very high peaks to plus infinity. So usually it is around the mean value, which may be something like 1 or 2 or so, but occasionally it goes out to very high peaks, for example, something like this, or something like this. So these are the exceptional places where you have once in a while very high peaks, and these are the ones which I'm interested in. Yeah. So therefore, I somehow stress that a bit too much. The picture is not really like this, because the distance between each 2 of them is enormously large, and the islets are really much smaller. I have to demonstrate what I want to tell you.
This is the picture of the potential.
This is a potential psi. I'm looking at the Laplace operator plus psi, and psi is an i.i.d field. And this here is a realization of psi.
Laplace is Laplace or minus Laplace?
Can you read this? So Laplace operator applied to some function f upon z is the discrete one. So take a sum over z, take the which are
He hasn't put the sign in yet. Let's just see what he wants to do.
So this is what I call the discrete Laplace operator. We had something like this already on the blackboard in Mr. Eisenstein. It's the, if you accept that this one is the discrete Laplace operator, by all standards, by all means, this is a discrete, the simplest discrete counterplay of the continuous Laplace operator. There is certainly also a statement like that under diffusive scaling, this one converges to the usual Laplace operator. But many other discrete ones do as well. And if you now look at this one applied to a constant, if you put this one equal to 0, and you bring the right-hand side, something is missing, certainly. 1 over 2d is missing, yeah? Then this term, which does not belong to the sum here, can be taken to the other side of the equation, then you get the mean value property. Yeah, I mean here this number of summons is precisely 2d. I'm working in ZD.
My main question was about the positivity.
Yeah.
Was it positive?
Yeah, okay. But I found it good to write down the array operator in place.
Thank you.
Yeah. So harmonicity with respect to this operator here is the same as mean value property. You see it now better.
Can I ask a question about
Yeah.
this function? How is the spectrum? Is it continuous? The spectrum is spatial frequency. If my language
spectrum?
understandable. If I take the Fourier transform of the autocorrelation function of that function,
I never do, by the way. Yeah.
this is okay.
Yeah.
What do I get? This is what we call the spectrum in optics, for instance.
The spectrum. So
But you understand, it's a distribution of frequency. If you think of a spatial Fourier transform of that, okay, but because it's random, rather than doing the Fourier transform of that, we do the Fourier transform of the autocorrelation function. Then you get the spectrum. My question is the spectrum continuous, discrete, has it a cutoff, etc.? In the case of the spectrum, for instance, it's very well defined.
So what will play an important role for me is that the top eigenvalues, the top spectral values are all eigenvalues, and I will be talking only about that. So the first 10,000 eigenvalues or so will be the object of my study and the corresponding eigenfunctions. 10,000 to be any fixed number, but not depending on L. L goes continuous.
So you have no continuous spectrum. That's, I think.
Yeah, so in a large box, of course, you have just the number of eigenvalues is just equal to the number of points in the box. This is linear algebra. Yeah, and that's all. So you are at the beginning, for fixed L, I have the discrete spectrum, and I'm looking only at the upper bound part, and this one stays point spectrum in the limit. Thank you.
Sorry for it.
Okay, so in this picture here, with the 0 being here somewhere, are interested in this, and in this peak, and I will make clear to you hopefully that they all correspond to one of the eigenvalues and with the corresponding eigenfunctions. I think this is completely known to you. So one eigenfunction, for example, should be concentrated in this area, another one here, another one there. And this one, even though it has a very high peak, it is not broad enough in order to carry so much mass of an eigenfunction. I would say this one may be the largest, this one the second, this one the third, and this one the fourth in this picture. And my desire is now to say more precisely something about how, what does the xi look like in these peaks. There's something which I can say about the limiting statement. Yeah, there's a deterministic shape, which I want to explain to you as well. A priori, this should also be a deterministic shape if it would be really a very good eigenvalue, but this one has obviously a different shape.
I have to interrupt.
Yeah.
So the choice of the sign, he just reversed because he's looking at the top of the spectrum rather than the bottom.
Yeah.
So
Yeah, these are wells.
these are wells.
These are wells.
Just
It's just whether the one that we know here.
Yeah.
Yeah, we will are
Bottom wells.
It's incredibly important to realize that the picture is
This is really the Laplace operator, no minus.
But this convention is okay, so but it's not good
Yes.
when you change to the top. Anyway.
Yeah. Yeah, you cannot repeat it often.
Yeah.
Yeah. So therefore, this is really what you also are looking at. And I will make some more precise assertions about the shape of the psi in those peaks which are really relevant. And I will tell you that there's also certain limiting statement about a limiting deterministic shape. Even though everything is, of course, i.i.d. and random. i.i.d. means independent and identically distributed. Yeah. Okay, so let's start now with the first slides. The first two slides are written for a different audience. I think you can tell me much more about this than I do.
Why are you saying parabolic?
Comes later.
Like
this is not yet there. Yeah, the time dependence is not yet there, but will be incorporated a bit later. So Random-Schrödinger operator is now this operator here, and this is the formula for the Random-Schrödinger operator, nothing new for you. And the two interpretations there, I think this is something which you can explain much better to me than I did to you, so just forget it. The prediction of Anderson and some most important statements about the mathematical proofs of this is also something which at least part of you can also explain much better to me than I to you. The two first slides are read for a different audience, for the probability audience. Yeah. So the prediction by Anderson of 58 has been mentioned a lot in this workshop here, and it has been mathematically proved in certain situations already. There are basically two proof methods. Fraction moment method is the name of one of them, and multi-scale analysis. And I think that Dirichlet must have explained them to you, and I'm not here to this day. And for me, the big open problem seems to be what is the matter with the eigenfunctions and eigenvalues outside the region where you know that there is Anderson localization. What are extended states? So, but this is only a side remark. This has nothing to do with my talk. Even though we'll be looking at localization, I think this is not what you call Anderson localization, because these effects that I'm going to explain to you come from a large box and something which you call extreme value statistics. So this will be one of my most important methods here. I will make a precise analysis of the statistics of extremely high values of the potential psi, and they in turn will tell me something about the spectrum. So this is something for which I need a large box and L to infinity, and then I can make asymptotic assertions with the help of extreme value statistics. And then I come to very precise assertions. But this is not what you call Anderson localization, because it is not possible to pursue this on ZD immediately. But certainly it has much to do with it. Okay, we are interested in the upper edge of the spectrum in a large box B. And here I wrote down the principal eigenvalue, but this is not the only one which I'm looking at. This is the sometimes called so-called Rayleigh-Ritz principle. I wrote it down in continuous terms, yeah, but you can also write it in terms of a sum, then it applies to the Z either setting. Now we introduce all the eigenvalues. Lambda 1 is the largest, then lambda 2, lambda 3, and so on. And there I'm not absolutely sure anymore whether they cannot coincide or do. At least in continuous terms. And here are my main questions for the beginning at least. What is the upper tail behavior of lambda 1? In particular, when you couple it with B, with the box going to infinity. What is upper tail behavior? I want to look at the probability that the eigenvalue is larger than a certain number, and the number goes to infinity. In the asymptotics, as this number goes to infinity. What is the probability, the behavior of the first eigenvalue being small?
That's a Lipschitz tail. This is a Lipschitz tail for you.
This has very much to do with Lipschitz tails, yes. I'm here in the world of extreme value analysis, or Lipschitz tails, or large deviations. You can use either term you like, depending on where you come from.
Except that the potential is not bounded below here.
Yeah, this is also important to point out. There are pictures also, I will comment on this later, for bounded potentials. They have basically the same structure, but you don't see so precisely anymore because high peaks are easy to write down. But the same picture, much of what I'm saying here is also true in the appropriate sense for bounded potentials, for example. Second question, is there an extreme value order statistics for the eigenvalues, for the top eigenvalues, I mean the first one, the third one, the second one, the fourth one, and so on and so on. If I take them as random variables, a priori they're certainly not independent, but they are as if. Yeah. Do we have a similar behavior as if they would be independent? Maybe it's good to jump to this general statement from the literature of extrinsic statistics. So the main assertion there about extrinsic statistics is the following. So you have n independent random variable with the same distribution, call mn the maximum of them. And if you have some an and bn, so you want to normalize them some way, the maximum typically goes to infinity, at least for my case it goes to infinity. You subtract something which gives you, which fetches the random variable down to some finite size, and then you divide by something, and if you find the right values of an and bn, such that this one converges to something interesting, of course, yeah, then there are only 3 different possibilities of the limiting distribution. And these are called Gumbel distribution, Fréchet distribution, or Weibull distribution, depending on which distribution you started with. Yeah. So this is a general statement about extreme value statistics. Something like this is what I have in mind for the eigenvalues, even though they are a priori non-independent. And another thing is you can write down a limiting statement for the point process. The delta measure is the Dirichlet measure. Yeah. So you take the sum over the delta measure in all these points xk minus with the normalization. And this is not a probability measure. This is a point measure which puts a point at each of these shifted and normalized random variables xk. And this point process converges to something which is a certain process for the Gumbel case, a certain process for the Weibull case, and a certain process for the Fréchet case. Yeah. It is not that all these points here survive in the limit, because most of them will go to minus infinity and are off. Only the top one stay over, survive in this limit, and only they give you some interesting limiting statement. Okay, so I tried to find something like this for the eigenvalues. Yeah, what is the domain of attraction? I mean, these 3 here are the 3 possible domains of attraction. And what are the scaling parameters an and bn? And does this corresponding point process converge? After normalization, of course. I mean the normalization here with an and bn. And are the corresponding eigenfunctions exponentially localized? If yes, where are the centers of the localization? What can you say about the centers of the localization? The last question can already be answered, I would say, because everything is completely independent and homogeneous. So there's no reason why here is a better place for having a high peak than here, because everything looks everywhere the same. So therefore, the set of center points where the eigenfunctions are localized must be a Poisson point process. The standard Poisson point process, homogeneously, independently thrown points into the box. Yeah. So if something comes out, then a homogeneous point process for the location centers, for this location of the centers. So here's now my motivation. I started with this equation here. This is the Parabolic Anderson model. You can call it the heat equation of random potential, and you can call it Schrödinger equation without I. Yeah. So it is just the same, but here's no I. Yeah. So this is entirely real, and therefore I thought many years ago, here I can do something with probability theory, because I don't have to look at the imaginary part and real part, and here I have a clear interpretation of a solution. Actually, the most important motivation comes from this sentence here, which I would like to explain to you a bit better. It's not important for what follows, but it gives me the motivation to look at it. So branching random walk in a field of random branching and killing rates. So the xi's are the branching rates and the killing rates. They can be positive and negative. Yeah. Take the positive part out. These are the branching rates, and the negative part are the killing rates. And now you start with one particle at the origin at time 0. This is expressed by this one here. I have a localized initial condition. One particle at 0 at the origin at time 0. And now this particle runs like a stochastic process called simple random walking continuous time. This one is the generator of simple random walking continuous time, which means after an exponentially distributed random time, it jumps to one of the 2D neighbors, to each of one with the same probability, 1 over 2D. But there's an additional mechanism, and this comes now from the random rates in that point where you are. You have now a killing rate, and you have a branching rate at the place where you are, and they tell you another exponential random time, after which this particle is either split into 2, branching, or is killed immediately, killing. And both can happen practically, and both these exponential times are running at the same time, and the one which is first, this one decides what you are doing. Actually, you have 3 exponential random times for each particle. No? One for the branching, one for the killing, and one for the migration. And the one which is giving you first its impetus, then its action is carried out, and then another set of random times start running. And each particle is handled in the same way independently. Yeah, so it may be that you produce a lot of offspring, more and more particles. And here in this case, you don't have killing at all, only branching. So the number of particles will go to infinity. And certainly, if a particle runs by chance to this place here, or to this place here, then the branching rate is enormously large, which means after short times, you have split, and therefore a lot of particles will be accumulated here, and will be produced there. Yeah. So therefore, these are the islands in which you should expect especially many particles in your branching process. And this is what we would like to understand more precisely. And now it comes, if you take the expectation over the migration mechanism, the killing mechanism, and the branching mechanism with fixed size, then U of tz is the expected number of particles at the point z at time t. So U of tz tells you on an average with respect to the random mechanisms, how many particles you should expect there. And if U is, if you have many particles here, for example, then you certainly expect that the U has also very high peak there. Yeah.
Sorry. Oh, I was skipping ahead. Wait.
Okay. Yeah, so this is something where you have to take an expectation. Certainly you can also go deeper and forget about the expectation, and then you look at the branching process itself. Also, some people have done this on the base of the knowledge about the Parabolic Anderson model, but this is not part of my talk today. Yeah. There's another interpretation which goes back to the simple interpretation of the equation as heat equation with random potential. It's, you can call it also a simple and fundamental model of random mass transport through a random field of sinks and sources. So sources means that a random mass can be larger. Sinks means that the random that the mass can vanish there. The negative part can even be sometimes equal to minus infinity. That's also possible. Yeah, then the mass immediately is killed. Hard killing is sometimes the motion for this. Okay, and for the solution, there are two important mathematical methods or mathematical formulas. One is the Feynman-Katz formula, who relates this with some random walk picture, but I don't need this formula in this talk, so therefore I don't write it down here. The more important one is this expansion in terms of the eigenfunctions. So if U is a solution in ZD, I don't have a box a priori, but I would like to have a box in order to have the solution theory and eigenvalues in a strict sense. And therefore, I first go down to some large box, which means zero boundary conditions outside the box. And this one here now can be written in terms of this eigenvalue expansion, and you can take for Bt, for example, this box here, if L is coupled with T somehow. Yeah. So sum over all k, e to the t times the kth largest eigenvalue, and then the eigenfunction at 0 times the eigenfunction at z. The box, yeah, you're a bit cheating. T times log T would be more appropriate, or T times log squared T or something like this. Not so important at this place here. Some a priori box which might be quite large.
But, sorry, this is my question.
Yeah.
I'm confused by the notation.
Yeah.
You don't mean the box expands with T, as opposed to...
The box depends on T.
It does expand. It does.
Yeah, it grows with T.
I didn't know if it was first coordinate T, second coordinate, something in the box.
This is T times, maybe cross is not the right thing. T.
Oh, I see.
Number
Two
times
T's.
box.
He wants you to fix
Yeah.
the box. He wants a fixed T.
Yeah, the T appears at two places.
I understand now.
T appears at two places, and this makes mathematically true. Yeah. Yes. But this is precisely what I mean. And this here means also really the strict sense. The quotient goes to 1. Yeah, in a strong sense. Yeah. The right choice of the radius of the box is a bit part of the technicalities that I would like not to go into. If you take T times log T, then you can easily prove that outside this cannot really contribute. And if you take T divided by log T, then you get a box in which you really have the strong statements. And you have to bridge somehow the small part between T over log T and T times log T. This is very technical. I don't want to talk about this.
Sorry, I think now we're open. Sorry. So it's a parabolic box, and it's not flat, right? You don't actually mean you take level T times minus 1 half, something like 0 T or minus T or...
The box goes from minus
It's in ZD. It's in ZD.
So it's just translation. T is just a translation.
It's just a big box.
It is if you yeah, the big box.
Okay,
That
never mind.
X is time.
So cross is just a multiplication. It's not addition of the
Yeah,
order.
the times is maybe not the right thing, but if I say that T times the box.
That.
Yeah. So it is as if you take the L depending on T, like T half, for example. Yeah.
There's no gradient dimension in CD
We
box.
would have just left that as L. And then you could say
Yeah.
L is...
T times 1/2 is L, for example.
Yeah.
And when you write that formula of phi sub k of z, that also depends on t.
Oh yes, yes. Should be mentioned. This one here depends on the box, not on T. It depends on not this T, but on this T.
Yeah, just one.
Yeah, this is important to know. The eigenfunctions depend only on the box, but not on the number T here. T appears 2 times.
The reason why people are confused is you have 2 rows for the letter T.
Yeah, but it has to have
Another name.
a priori, you don't have a box at all, no? But that I don't know which eigenvalue I should plug in there.
It's
No?
an approximation.
Yeah, that's an a priori box in which I can now really work with the help of linear algebra. So some heuristics, maybe some of them have already mentioned. No, this is an important point which I have not yet mentioned. Excuse me. If you go now to this formula and try to find the right answer, what happens now T to infinity? Then certainly you would like, I mean, this is the most important point where T appears. No? This is an exponential with rate lambda k of B, of the box. And therefore, the leading one, the biggest one, will certainly give you the main contribution. It's your first reaction. Yeah? But then you say somehow, moment, here's also a certain T dependence. Can it be something which interferes the answer? Yes. Is my answer. So let me try to explain it to you. It's not automatic that k equal to 1 gives the leading contribution. You really have to take all the leading eigenvalues and then you decide. And I think in this picture you see it a bit better. So do we have another color? Yeah, lots of colors, very good. So the leading eigenfunction is something like this here. To normalize, something like this here. It's everywhere positive. It is so small that I cannot really give it to you more precisely. No? So this should be the leading eigenfunction centered around the point where the leading, where it is concentrated. This belongs to the first one. And I would say, is this the second or is this the third? And I would say here's the second now. Something like this. This is something which is not everywhere positive. I would like to indicate it like this here. It has a few points where it is also negative. This might be the location center of the second eigenfunction, and maybe here is the third eigenfunction. It will be part of my analysis to convince you that these eigenfunctions here look pretty much the same to each other in distribution. They converge to the same limiting shape. And the limiting shape here, by the way, this is of final order. Yeah? So the island size, this is also an important question, how large are the islands? And the size of the islands depends very much on the distribution that you are looking at. And my particular distribution that I will discuss to you have the particular property that the islands are of finite size, not depending on T, not depending on L. Yeah, I'll comment this a bit later. So, but now, the interesting thing is here, because I have to evaluate each eigenfunction at 0. And if I just assume that the eigenfunctions decay exponentially fast, and they do, then the distance, of course, distance to the origin is important for the size of the sum phi k of 0. So if e to the minus some constant times the distance is the value at 0, then I would say the one which is closest has the largest phi k of 0 value. Yeah. While the one which is which gives you the largest eigenvalue is further away and therefore has here a smaller value at 0. So you cannot see it from the formula there, but it is mandatory at the beginning to take into account these two terms together and to take them, to order them in their size according to, this product of the two must be ordered, and it is not a priori clear that k to the 1 gives you the largest product. Yeah. And this means also for us that we have to take into account all top eigenvalues in order to see afterwards which one is the largest. And then you have the phi k of z for that k, which turns out to be the largest. Yeah, and for example, here could be the largest. And then this means that the u function is basically only concentrated here. And okay, so if we assume now that the third one is the largest, then my picture for the u function at a large time t is something like this here. U is not normalized. So this is u gamma naught, if L is t half. Yeah. So then I would say the total mass of u is asymptotically almost entirely concentrated in the peak where the best compromise between the eigenvalue and the closeness to the origin is realized. So this is my picture for the understanding of the solution as t goes to infinity. So therefore I have to get my information about all the eigenvalues and about all the locations of the eigenfunction centers. And this is what I'm going to do now. So now some comments which are practically done already. So the maximum of the number e to the t lambda k times phi k of 0 over k will be decisive. This is a function which I need to evaluate at the limit t to infinity. All the eigenfunctions decay exponentially fast away from the random side xk, as in the picture. This is what we have to prove. By the way, for proofs of things like this, we do not rely on methods from the theory of random Schrödinger operators, but we developed our own methods based on some random walk representations. And you will come, I hope I come to this at the end of the talk, that I can tell you what our main argument is for finding exponential decay. The main argument is, of course, that we first analyze psi and derive a precise picture as it is here. And then if we go away from the center, then we see that the eigenfunction goes exponentially far away with the help of a certain martingale argument. Very probabilistic. Good. So then the distance determines then the value of phi k of 0. And you see here there's something exponential also there. So it has to be considered together with the eigenvalue. These distances here are of order L, which is of order T. Yeah, so you should not neglect the distances. And I cannot say much about this proportionality factor C. I think it must also go to infinity slowly as a function of t, but I cannot really put my hands on it, I must confess. I'm still in the part of the talk where I give you some arguments, but this is not at any place the one in which I also derive proofs. Yeah. So actually this delicate part here is finally done with the help of probabilistic arguments, not with the help of eigenfunction decay. Yeah, but the I think for understanding what's going on there, it is perfectly suitable. Okay, this I already said something. I said something like this: the random sides of the localization center form a homogeneous Poisson-point process, and the eigenvalues behave as if they were independent, identically distributed, because their distance is far, and so therefore the correlation between any two of them is decaying to zero quickly. Yeah, the eigenvalue order statistics and the homogeneity of the x case give you good control also on this one here, because these are functions of all these limiting statements that I can express in terms of eigenvalue order statistics. If I have all these ones here under control, then I can do the maximization over k. And I do have with my assertion that I will go to formulate in later proof. This is also an important thing which I didn't want to make too much noise about now, but maybe it's better to explain you something about this. There was an earlier work about just one of these peaks. How can you describe the shape of the xi and of the corresponding eigenfunction in such a peak? And this is something which you call extreme value, large deviation analysis. So it was shown that the typical shape is deterministic, and we can also control it in terms of the variation problem. Maybe I try to explain it to you. Can everybody see this part of the vector? Certified here. So we take the probability of one of these random variables as e to the minus e to the r divided by rho, where rho is a parameter, and take this only for r to infinity. This is my distribution that I would like to talk about. This is sometimes called the doubly-exponential distribution. It's a very particular one. It is unbounded to plus infinity, but the tails are extremely thin. This is the interesting distribution which leads to discrete islands. I mean, islands which are not trivial. You could even make finer, larger tails at infinity, such that the islands are just singletons, which is a bit boring.
So rho is just a constant parameter?
Rho is a parameter in the game. Yeah, it's just a fixed number. No? So this is a distribution that I'm looking at. This is a particular one because the islands are then consisting of discretely many and finitely many points, not depending on L. This turns out in the analysis. So now I look at the probability that my field xi runs like rho times log k plus a potential shift. So in some box which we call now D. So I would like to know what is the probability that the potential looks like something which goes to infinity logarithmically in t plus a certain shape. Like in the picture, huh? So you first have to go up to rho times log t, and then on top of it you have some deterministic picture. This is easy to calculate now.
I don't see where the parameter t is.
T goes to infinity.
What is xi was the
write it down as distribution. So I have an equation for all points x in the box D. I take some box, And here I've got psi of x is roughly, also is equal to or roughly equal to rho times log t plus phi of x. Phi is the potential. Yeah. So think of phi here, huh? So this is the phi, so to speak, and here, so to speak, I have my ht, yeah, which goes somehow to infinity. Yeah. So I look at everything which is beyond certain threshold, which goes as t goes to infinity, no?
So your dependence on t in that formula is in the domain d?
The domain is fixed and t goes to infinity.
Wait, but then c doesn't depend on t, phi doesn't depend on t, what depends?
So this is random. This is just a number which goes to infinity, and this is a potential shape, a deterministic potential shape. For a given phi, I would like to calculate now this probability.
But t goes to infinity.
T goes to infinity. I want to make asymptotics as t goes to infinity. Yeah. Maybe at the end of the calculation, you know what I really want to have. Yeah, I want to show that this probability goes exponentially down to 0, and I can precisely nail down the probability decay of this.
C is a random.
C is my potential.
C is a random variable. It's independent of each side.
Yes, independent.
And the phi is a deterministic.
Phi is deterministic, yes.
Phi is deterministic.
Yeah.
This seems like a ridiculously rare event here.
Yes, you're right. This is what we have to do. Because I'm looking at very rare things only 4 times in 2 meters. Yeah. And therefore I have to look at extreme things. This is the A and O of my theory.
But you're asking that this be true for the entire domain.
In the domain D, and D is some fixed size.
Oh, it's a subset.
It's a subset, yes.
It's a piece of the entire.
For example,
it's a chunk.
For example, this is D. Just a
some
part.
specific piece.
Yeah. What is the probability to see in some subset D is such a potential?
But now there's the overshoot, which is peculiar that I see.
Yes, a large number plus an overshoot, which is deterministic. Yeah. And I can calculate this easily. Yeah. So first of all, I take this product out. And then I take my formula there. This is only approximation, but it is good enough. Yeah. I take now this formula, e to the minus, e to the 1 over rho, and here I plug in the r, which is now this one here, rho log t plus 5x. So e to the minus, e to the, yeah, so this is a very particular function. This is just now elementary calculation. I take the product into the summation. So this one here gives you just a t, and then I can take the sum over x of e to the minus 1, no, that's 1 over rho of x. So we're seeing now if I define this here as i.d, of phi, that I have derived something which is called the large deviation principle. I found the exponential decay of the probability that my potential looks like that what I see in the picture. Yeah. It decays exponentially fast, and the rate of it is this one here. So this function here tells you something about how likely it is to see such a shape in my big picture somewhere. And what you have to do now is to adapt the t from there to the size of the box. Yeah. And then if you adapt it in a proper way, then you can say, if I choose the parameters in such a way that I see just finitely many of that shape here, then you will finally end up only with those ones which optimize the I of phi. Yeah. So a certain optimization is there. You have to also to relate it to the lambda phi, to the eigenvalue that comes from the phi. Yeah. So this is behind this one here. So the lambda phi gives you the value of the local eigenvalue, and the I of phi is somehow the payoff for the small probability that you have for this potential phi. And therefore you have to optimize this one here, and the minimizers, the optimizers of this one, tells you which shape you really find in the leading eigenfunction peaks. Yeah. So imagine that this one here or this one here is really shaped like the maximizer from here. And then you have the answer.
So you did this with a probability that's i.i.d double exponential?
Yeah.
If you had other i.i.d. probability distributions, can you
Yeah,
do the same
yeah.
computation?
Here's the literature. So this class is one of 4 important classes. So there are surveys. I wrote a book which is more or less an extended survey of everything about the parabolic Anderson model. And Avidas Astrauskas did this about the same time as well. And he did also eigenvalue order statistics and Poisson-Point process convergence for those distributions which lead to single point peaks. And this is what I would like to give you in my talk now. And interesting is also that people from the theory of random Schrödinger operators did eigenvalue Poisson-Point process convergence also in the bulk of the spectrum. And I think the best assertions are by Germany and Klopp. And concentration in one single site have been worked out in a number of papers for different distributions. And in one non-degenerate island is what I would like to tell you now. And there's a recent paper for bounded potentials. This is maybe your question. So you would like to know, for example, what's the matter for potentials which are just 0 and 1, for example. Bernoulli random types. And this has been worked out by these 2 guys here recently, has not been published, yeah. But they do not really show Poisson-Point process convergence, but just concentration in one island. Yeah, for the t-dependent.
And these references also deal with the shape of the eigenfunction.
This tells you something about the shape of the eigenfunctions. I have the feeling they can do better, but they did not. It's technically always involved, so such that people are happy also with less information. But I'm pretty sure you must be able at the end of the day to prove that the leading peaks have a very particular deterministic shape. Yeah, we did it for our distribution, and I think they did not do it for their distribution. There's still something open, but I'm absolutely sure it is true. Yeah. Let me come to the first assertion. Let me formulate it. Yeah, but it's fine. It's fine. So there's a number chi which comes from this optimization of the eigenvalues against the large deviation rate function I of phi there. Yeah. And there's a sequence of ALs which goes like that here. This is roughly rho times log L. It goes to infinity. Minus the number chi. And then you have the following for each top eigenvalue. The L2 norm, they are L2 normalized, of course, no? But if I take the sum of them only in the log L neighborhood around the localization center, then I still get 1 in the limit t to infinity. This corresponds to the picture here. No? So if I take such a box here, then the total mass of the green function is already 1 for each k. And here's the eigen. This is a point process convergence. So the normalized centers I have to divide by the size of the box. And here is the shifted eigenvalue. So I have to subtract this AL, and then I have to normalize with log L, and then I get some convergence to something. And the something is a Gumbel distribution. So the Poisson-Point process has total homogeneity with respect to space, and it has the Gumbel distribution signature for the eigenvalues. So we are in the Gumbel case. And now the second theorem, applying this to the time-dependent solution. So far it was only about eigenvalues, no time, and here's no time. I go to the time-dependent solution. Yeah, I have to insert such a thing here, L times log L, log L. Also goes to infinity. And then I look at this function here. So this here comes just from the homogeneity of the points. This is spatial. And this comes from the shifting and normalization of the eigenvalues. Yeah. And you take now of your points this function there, and you take the k such that this is maxima. This is nothing but the optimization over k after rescaling. Then the total mass, 1 over u of t is the total mass of everything, and here I take only the sum of the u's in the neighborhood of the optimal xk. This is what I have here, no? Maybe I do it in red. So the mass, the partial mass coming from some island goes, also is asymptotically the same as if I would sum the U over everything, as I announced. So that's just a formulation of it. So I think I commented already so much that I could easily stop now. This is really, these are the main assertions that I would like to give you. There are 3 more classes of distributions which have been partially analyzed but not in such a full strength. This is the easiest, so to speak. Yeah. And I'm pretty sure that for the other classes of distributions, everything like this is also true, but you have to work it out and you have to find the very precise objects in terms of which you can write it. And you have, partially you have to also to find new proofs. I think those will come in the next couple of years. Yeah, I'm absolutely convinced that it's also true for the other distributions. For example, bounded distributions, which have been done almost by the 2 Chinese guys, and there are 1 or 2 other distributions for which nobody has it done yet. Yeah. Okay, thanks.
It's more of a happy comment that this is really absolutely perfectly fitting what we might be able to address with the landscape setting. Point blank, there is probably nothing closer than that. Yeah. Because what landscape is thrown is, where landscape is thrown is really at the beginning of the spectrum for sure. Yeah. I mean, we are hoping and we are fighting for seeing it often for mobility and things like this, but there is no doubt that we understand very well what happens at the beginning of the spectrum. And it looks like, actually it never occurred to me to look at this, but it looks like your setup is the perfect tool to emphasize the beginning of the spectrum. So, sort of both ways. I mean, I'm not saying that we can prove your terms, we can prove anything. But it's sort of a perfect way of communication, and vice versa. The results that you are getting are more or less square with the results that we need. For example, the deterministic shapes and things like this is something that we really would want to know even in semiconductors, because that's the shape of your world, the extreme case, and that's what determines the density of states and things like this. Actually, they are the same silently 5 seconds ago. Yeah. But really, I mean, this is both ways of communication. This is really squarely very well fitting what we are trying to develop.
If you want to know more about the continuous, spatial continuous case, where, for example, for some point process, and around each point, you take a ball of radius 1 and put it potentially to 2 minus infinity there. I can switch the sign again.
Yeah, I'm not good at the ball signs. I mean, this is a language.
This is also interesting for you, and this has been analyzed in detail in the 90s by Alan Saltzman. So for this particular case, you get much information and precise formulas from him. Not such a result here, yeah, but much information about it, which can be also extended to something like this. Yeah. So he wrote a book about this, huh? So his name. So he worked on the spatially continuous case with Brownian motion among Kosanovsky books, which may be also interesting for you.
Can you recover his results through yours by a homogenization process or something?
No, nothing is homogenization. There's no homogenization here.
Oh, I know that.
What is it?
I'm asking if you let your scale go out to infinity, and then think about it as decreasing your step size instead, can you recover his results from your results?
His results?
Yeah, because you said he did a similar analysis but in the continuum. Yes.
It is possible, but has not been done. So what does the 4 classes of distributions distinguish from each other? First of all, you have to take an appropriate scaling, and then you have to find an appropriate counterplay of the area phi, the rate function, and then you have to write down the corresponding variation formula and discuss its properties of the minimizers. And then I'm sure you can let the variation formulas converge after rescaling to the other variation formula, and then you have described in the terms of variation formula the transition from one class to another class. And then I think you can also make probability out of it. But this has not been done yet. Yeah. the transitions between the classes.
I have a quick question. I think that what we call the landscape in probability theory is called the average escape time or the mean escape time. Or so I've seen this. This doesn't play a role. You never use this concept for for the random walk.
There is always the Feynman-Katz formula behind it, and it is often considered after a certain exit time from something. And this plays a role in fine proofs inside smaller balls, in which you would like to describe the eigenfunction with the help of random walks. There, I guess you can use something like this, like the escape time.
Maybe a way to.
Yeah, but this is a technical detail, Marek.
Okay.
Yeah.
No other questions, and we thank the speaker again.